Hello, my name is Ismael.
Hi, I am Rifai. And my name is Lydia. We are from Group Omega. This video is about deadlock.
This is our video for our operating system assignment.
Deadlock. What is deadlock? Deadlock is a situation, typically one involving imposing party in which no process can be made. Under the normal mode of operation, a process may utilize a resource in only the following sequence: request, use, release. Request. The process requires the resource. If the request cannot be granted immediately, then requesting process must wait until it can acquire the resource. Use. The process can be operated on the resource. Release. The process release the resource. Characterization. A deadlock situation can be arise if the following four conditions hold simultaneously in a system. Mutual exclusion. At least one resource must be held in non-shareable mode. That is, only one process at a time can be used the resource. If another process requires that resource, the requesting process must be delayed until the resource has been released. Hold and wait. A process must be holding at least one resource and waiting to acquire additional resources that are currently being held by other processes. No preemption. Resources cannot be preempted. That is, a resource can be released only voluntarily by the process holding it. After that process has completed its task. Circular wait. A set P0, P1 until P11 of waiting processes must exist such that P0 is waiting for a resource held by P1. P1 is waiting for a resource held by P2 until Pn minus 1 is waiting for resource held by Pn, and Pn is waiting for a resource held P0. Method for handling deadlock. Generally speaking, we can deal with a deadlock problem in one of three ways. Number 1, we can use a protocol to prevent or avoid deadlock, ensuring that the system will never enter a deadlock state. Number 2, we can allow the system to enter a deadlock state, detect it and recover. 3, we can ignore the problem altogether and pretend that deadlocks never occur in the system. The third situation is the one used by the most operating systems, including Linux and Windows. It is then up to the application developer to write, program and handle deadlock. To ensure that deadlocks never occur, the deadlock can be used either a deadlock prevention or a deadlock scheme. Deadlock prevention provide a set of methods to ensure that at least one of the necessary conditions cannot hold. This method prevent deadlocks by constraining how requests for resources can be made. Deadlock avoidance requires that the operating system can be given deadlock avoidance requires that the operating system be given additional information in advance concerning which resources a process will require and use during its lifetime.
I will explain deadlock prevention. Deadlock prevention algorithm ensures that at least one of the necessary conditions, which is mutual exclusion, hold and wait, non-preemption, and circular breaks, does not hold true. However, most prevention algorithms have poor resource utilization and hence result in reduced throughput. Mutual exclusion. Not always possible to prevent deadlock by preventing mutual exclusion, making all resources shareable as certain resources cannot be shared safely. Hold and wait. We will see two approach, but both have their disadvantages. A resource can get all required resources before it starts execution. This will avoid deadlock, but will result in reduced throughput as resources are held by process even when they are not needed. They could have been used by other Second approach is to request for a resource only when it is not holding any other resource. This may result in a starvation as all required resources might not be available freely always. For preemption, we will see two approaches here. If a process requests for a resource which is held by another waiting resource, then the resource may be preempted from the other waiting resource. In the second approach, if a process requests for a resource which are not readily available, all other resources that it holds are preempted. The challenge here is that the resources can be preempted but only if we can save the current state, which save and process could be restarted later from the save state. Circular wait. To avoid circular wait, resource may be ordered and we can ensure that each process can request resources only in an increasing order of these numbers. The algorithm may itself increase complexity and may also lead to poor resource utilization. Next is deadlock avoidance. As you saw already, most prevention algorithms have poor resource utilization and hence result in reduced throughputs. Instead, we can try to avoid deadlock by resources by processes including resources available, process allocated, future requests and future releases by processes. Most deadlock avoidance algorithms need every process to tell in advance the maximum number of resources of each type that it may need. Based on all of resources of each type that it and all this info, we may decide if a process should wait for a resource or not, and thus avoid chances for circular waits. If a system is already in a safe state, we can try to stay away from an unsafe state and avoid deadlock. Deadlocks cannot be avoided in an unsafe state. A system can be considered to be in safe state if it is not in a state of deadlock and can allocate resources up to the maximum available. A safe sequence of processes and allocation of resources ensure a safe state. Deadlock avoidance algorithm try to allocate resources to a process if it will make the system in an unsafe state. Since resources allocation is not done right away in some cases, deadlock avoidance algorithm also suffer from low resource utilization problem. A resource allocation graph is generally used to avoid deadlocks. If there are no cycles in the resource allocation graph, then there are no deadlocks. If there are cycles, there may be a deadlock. If there is only one instance of every resource, then a cycle implies a deadlock. Vertices of the resources allocation graph are resources and processes. The resource allocation graph has request edges and assignment edges. An edge from a process to resource is a request edge, and edge from a resource to process in allocation edge. Come denotes that a request may be made in future and is represented as a dashed line. Based on come edges, we can see if there is a chance for a cycle and the ground request if the system will again be in a safe state. Resource allocation graph is not much useful if there are multiple instances for a resource. In such a case, we can use Banker's algorithm. In this algorithm, every process must be dealt upfront the maximum resource of each type it needs. Allocation of resources is made only if the allocation ensures a safe state. Else, the processes need to wait. The Banker's algorithm can be divided into two parts. Safety algorithm, if a system is in a safe state or not. The resource request algorithm make an assumption of allocation and see if the system will be in a safe state. If the new state is unsafe, the resources are not allocated and the data structures are restored to their previous states. In this case, the processes must wait for the resource.
Deadlock may occur if the system does not employ either a deadlock prevention or deadlock avoidance algorithm. The system may provide an algorithm that examines the system to check whether a deadlock has occurred, or an algorithm to recover from the deadlock. If all resources have only a single instance, then we can define a deadlock detection algorithm that uses a variant of the resource allocation graph called a wait for graph. We obtain this graph from the resource allocation graph by removing the resource nodes and collapsing the appropriate edges. A deadlock exists in a system if and only if the wait for graph contains a cycle. To detect deadlock, the system needs to maintain the wait for graph and periodically invoke an algorithm that searches for a cycle in the graph. The wait for graph sim is not applicable to resource allocation system with multiple instances of each resource type. When should we invoke the detection algorithm? The answer depends on two factors: how often the deadlock occurs and how many processes will be affected by deadlock when it's happened. If deadlock occurs frequent, then the detection algorithm should be invoked frequently. Resources allocated to deadlock process will be idle until the deadlock can be broken. In addition, the number of processes involved in the deadlock cycle may grow. Deadlock occurs only when some process make a request that cannot be granted immediately. This request may be the final request that completes a chain of waiting processes. If the detection algorithm is invoked at arbitrary point in time, the resource graph may contain many cycles. In this case, we generally cannot tell which of the many deadlock processes caused the deadlock. When detection algorithm determines that a deadlock exists, several alternatives are available. The first way is process termination. To eliminate deadlock by aborting a process, we use one of two methods. The first method is abort all deadlock process. This method clearly will break the deadlock cycle, but at great expense. The deadlock process may have computed for a long time, and the result of this partial computation must be discarded and probably will have to be recomputed later. The other way is abort one process at a time until the deadlock cycle is eliminated. This method incurs considerable overhead, since after each process is aborted, a deadlock detection algorithm must be invoked to determine whether any process are still deadlocked. Aborting a process may not be easy. If the process was in the midst of updating file, terminating it will leave the file in an incorrect state. For example, if the process was in the midst of printing data on the printer, the system must reset the printer to a correct state before printing for the next job. A partial termination is used. Then, we must determine which deadlock process should be terminated. The termination will occur on the process with minimum cost, but the problem is the term minimum is not precise in the computer system. To eliminate deadlock, using resource preemption, we successively take away some resource from process and give the resource to other process. Until the deadlock is broken, this usually occurs when one process is given enough resource to be able to complete the then frees up all of the resource it was using. Before we do resource preemption, there's three things we need to reconsider. The first is selection of a victim. Which process can have resource taken away from them easily? The goal here is to minimize cost. If a resource can be taken away from one process much more easily, then identical resource can be taken away from another process. We select the victim that we will have the easiest time removing the resource from. The second is rollback. If we preempt a resource from a process, what should be done with the process? If a resource is taken away, it obviously cannot continue in its current state. It would be much as I chop one of your legs and expected you to walk normally. One thing we can do is roll the process back to a safe state where the resource has been taken up by the process yet. Unfortunately, most operating systems don't have the capability to store state of process as they progress. Normally, and it is often impossible to determine the safe state given just the current state. The solution is a total rollback, aborting the process and starting from scratch. A total rollback is usually a last-ditch resort, only usable if a deadlock cannot be resolved without a total rollback. The third is starvation. This happens when the same process is chosen again and again as a victim, making sure that the process can't even finish. To prevent starvation, an operating system usually limits the number of times a specific process can be chosen as a victim. That's all for our video.
We hope that you understand about our topic deadlock.
Thank you for watching this video.
Hello, my name is Ismail.
Hi, I am Hi, my name is India. We are from Group Omega and we will talk about this video is about deadlock. This video is about deadlock.
Practice dulu ah. Practice.